Hello, I'm Daniel Awan, an application engineer with Yokogawa Test&Measurement, and today I'll be discussing different uses of our free space optical jig setup. Engineers using propagating light cannot use an optical spectrum analyzer without the use of some extra tools. Often, the engineers will need to couple the light into an optical fiber to connect to the OSA. In order to better support our customers, Yokogawa is offering reference materials and procedures recommended for measuring the emission spectrum of various light sources propagating in free space or the optical transmission spectrum of an optical filter. With multiple testing needs, engineers need to use a variety of light sources with unique properties such as wavelengths, frequencies, and photon energy. Also, the light sources are needed to validate properties of passive components such as optical filters, mirrors, and lenses. With our customers in mind, Yokogawa has developed a free space light measurement jig setup that will allow customers to measure different light sources regardless of their properties. Advantages of this setup include a diverse range of testing applications from various wavelengths, fibers, and light sources. Typically, engineers will use two types of light sources, divergent light and collimated light. Divergent light consists of light rays that spread while propagating. Collimated light is composed of light rays that travel in a constant diameter beam and do not diverge. In order to maximize the power coupling, the signal needs to be carefully aligned to the fiber input using the OSA's power reading. The free space light measurement jig setup allows for flexible arrangements, enabling the customer to change between using a collimated or divergent light source. To demonstrate one function of the free space light measurement jig, we will be using a signal many people are familiar with from a smartphone's facial recognition system. The phone contains a module called the flood illuminator that emits an infrared light that we would like to capture with the OSA. Besides facial recognition, some smartphones actually use a LiDAR sensor to detect object distances to aid with camera focusing in the dark. The setup is mainly comprised of a mirror mount that holds a parabolic mirror along with a fiber and aspheric lens held in different cage plates. To get the maximum signal, the phone needs to be placed as close as possible to the aspheric lens without touching. Aligning the fiber input, the mirror mount, the aspheric lens, and the phone will achieve a signal. With everything in alignment, the OSA and jig captured a wavelength near 940 nanometers from the VCSEL and LiDAR signals. Another function of the free space light measurement jig is measuring TO-CAN light sources. Place the optical output of the TO-CAN fixed in a cage plate as close as possible to the aspheric lens mount without letting the two touch. We will need to adjust the position of the optical mirror mount and the optical fiber end face so that the power measured by the OSA is maximized. After aligning the laser output, the OSA and jig can capture a 850 nanometer wavelength from the TO-CAN. These methods only show a few applications possible with this setup, but due to its flexibility and low cost, customers are free to customize it however they like for their testing needs. For even more information about light source measurements, please contact us at tmi.yokogawa.com. Thank you for watching.